Okay, in this lesson, we're going to simplify expressions that contain radicals. And the rules of radicals are going to come fast and furious. So hold on to your hats. Try to pay attention. Hey. Okay, there are two numbers that when you square them, you get 25. What are they? 5 and -5. Why did I write 3? 5 and -5. Okay. So in general, all positive numbers have how many square roots? 2. Okay. One of them is blank and one of them is blank. Positive and negative. Right. So keep in mind, though, when I write that radical symbol over 25, that means strictly the positive square root of 25. So if I write radical 25, I'm only looking for positive 5 as the answer. And everyone is only looking for that. Okay. Okay. That is called the principal square root. So square root vocabulary also includes terms like radicand, index, and radical sign. Okay. So for this symbol right here, x, whatever's under the square root, is called the radicand. The little n, the little number that sometimes shows up there, is called the index. And this symbol right here, that's called the radical sign. All right, so let's look at some examples of radicals that are not square roots, but different roots other than square. Okay. So I want to find the cube root of 64. That means I'm looking for a number that when I cube it, or when I multiply it by itself 3 times, I get 64. What do you think? 4. Yeah, because 4 times 4 times 4, 4 times 4 is 16, times 4 is 64. Okay. So the answer is 4 because 4 cubed gives you the 64. 4 is the number. When you cube it, you get 64. All right, how about the 4th root of 16? A number that when you multiply it times itself 4 times, you get 16. 2, right? 2 because 2 times 2 times 2 times 2. 2 times 2 is 8. Sorry, 2 times 2 is 4, times 2 is 8, times 2 is 16. So if you think of the cube root of 64 equals 4, if you rewrote that 64 as 4 cubed, right, those two things are the same, right? So if you take the cube root of 4 cubed, you get 4, right? And that turns out to be true in general. Cube rooting undoes cubing. So in general, if you take the cube root of x cubed, what do you think you get? X. You get the x back. Cube root of something cubed is just the something. So what do you think the 4th root of x to the 4th is? X. Yes, Kevin. Oh, okay, thanks. Okay, so now we're going to use that general principle here. We're going to try to figure out what the cube root of x to the 21 is. Okay. So remember, cube rooting x to the 3rd is easy. Cube root of x cubed is easy. It's just x. So I'm going to rewrite the cube root of x to the 21 as the cube root. No, it says 21. Okay. Yeah. Yeah, sorry, it's little. Okay, so I'm going to rewrite x to the 21 in a fancy way. Okay, I'm going to rewrite it in a fancy way that helps me. And I want to write it that involves something with a cube. I want to have something cubed because it's easy to cube root something cubed. So I'm going to rewrite x to the 21 as x to the 7th cubed. Does everybody agree that that's true?
It's a multiple, right?
Yeah, because last class we talked about when you raise a power to a power, you multiply the exponents. So instead of writing x to the 21, I wrote x to the 7th cubed because 7 times 3 will give me the 21. Okay.
My cubes will cancel out.
So now your cube root and your cube cancel, and you just get x to the 7th. Yeah, so there's a shortcut, right? We had a cube root and a 21. You could get that 7 by just dividing the 21 by the 3. But again, you don't ever have to remember the rule because we just answered the question without the rule, right? So you can use the rule if you want, or you can write it out and figure out how to get x to the 7th. Okay. So this is the general rule. If you want to eliminate a radical sign in the nth root of x to the k, if k is a multiple of n, you can just divide, right? So let's say I want to do the 4th root of x to the 20th. The answer is 5? X to the 5, yeah. So if I just use the rule, I would do 20 divided by 4 and I'd get x to the 5th, right? And that's the answer, yeah. But let's say you forgot the rule, like, oh, I'm not sure, do I divide, do I subtract, what do I do, I don't remember. So instead, I'm going to rewrite 4th root of x to the 20th. I'm going to rewrite x to the 20th as something to the 4th, right? I want to do something to the 4th so that my 4th powers will cancel. What goes in here? 5. X to the 5. Because x to the 5th to the 4th, multiply the exponents, you'd get x to the 20th. So x to the 20th is just rewritten as x to the 5 to the 4. And then my 4th roots cancel, my 4th root and my 4th power cancel, and you just get x to the 5th. Okay, so you can either write it out or you can use the rule. Okay, I want to simplify each of these. When you're under a square root, that is like there's some imaginary parentheses there, so you should do what's under the square root first. What is 9 times 4? 36. So this is the square root of 36, which is 6. Good. All right. What about the square root of 9 times the square root of 4? Here I'm going to do the square rooting first. What's the square root of 9? What's the square root of 4? Which is 6.
Is it always going to work out like that?
Always going to work out like that. If it's multiplication, right? If it's addition, this rule does not hold. But with multiplication, you can always break up the square root or put the square root back together, whichever is more helpful. So that's what's written here for product rule for radicals. You can multiply first and then take the square root, or whatever root, or you can take the roots and then multiply. Same thing with fractions. You can take the radical of the whole fraction, or you can break that radical up and do the radical of the top over the radical of the bottom. All right, so here I've got like a sort of a complicated looking radical expression. I want to simplify it. Okay, this is going to be tough. There's going to be a lot of steps. And what I think makes these problems tough is that there's always like 3 or 4 ways that you can get to the same answer. So there isn't like the way. So as long as you are following the rules, like you might do them in a different order, but you'll be okay. All right. So first, my hint is use the product rule to combine the 2 radicals into 1. They're both cube roots, so I can put both radicands under one big radical sign. Right? That's what we just looked at with the 9 and the 4. So first, I'm going to do one big radical sign, and I do 16x to the 4th times 2x to the 19th. Right? So I combined it into one big radical, and sorry, it's a cube root. Okay, so next I'm going to multiply the numbers and multiply the x's. What's 16 times 2? 32. And what is x to the 4th times x to the 19th? X to the 23rd, yeah, right? Multiplying like bases, you add the exponents. Okay. So here's the step where it gets tricky. I'm going to refactor into perfect cubes and whatever's left over. So this is the hardest step. We have to ask ourselves, is there a perfect cube? So it might help you to have that sheet that I gave you. Perfect squares, perfect cubes, perfect 4th powers. Right. Because I'm cube rooting, I want to find things that are perfect cubes, right? So here's my cube root. 32. Look in your list of perfect cubes. Are there any numbers in that list that divide evenly into 32? 32 goes into 64, but not the other way around. Looking at the perfect cubes, the third column over, perfect cubes. There is one. 8. 8 goes into 32, right? How many times? 4. 8 times 4 is 32. So I'm going to rewrite my 32 as 8 times 4. And I rewrote 32 as 8 times 4 because 8 is a perfect cube. Okay. All right, now x to the 23. I want to rewrite that in a fancy way that makes it easy to take a cube root, right? So a couple minutes ago, we were able to take the cube root of x to the 21st, right? We did that just a couple minutes ago. Cube root of x to the 21st was x to the 7th. Here it is. Yeah, cube root. Yeah, 23 is prime, which means you can't divide it by 3. But I can do something fancy, right? And instead of writing x to the 23rd, I could write x to the 21, because I know I can cube root that. And then what do I have to multiply by? X to the 2nd, yeah, because 21 plus 2 would give me the 23. All right, good. So I split up the x to the 23rd into x to the 21 times x squared. And the reason I chose that particular split is because I know that I can cube root x to the 21st. So this definitely takes some practice in being able to recognize what you can cube root, what you can square root, right? It takes a little work. We're just being clever, tricky and clever, okay? So now I'm going to use the product rule to rewrite this as 2 radicals. One where I keep all the things that are easy to cube root, and one where I put all the things that are hard to cube root. So this is going to be a cube root times a cube root. So I'm going to grab the things that are easy to cube root, like the 8 and the x to the 21, and put them in here. And the things that are left over are going to be 4 and x squared. All right, last thing is that now I can actually take these cube roots. What's the cube root of 8? 2. What's the cube root of x to the 21? The answer is 7. X to the 7. Right, and then this I can't simplify any further. I can't take the cube root of those numbers. So this is just going to stay the cube root of 4x squared. There's a lot of steps, right? There's a lot of steps. And you could have done them in a different order. There might have been something that occurred to you to do differently. And often that's okay, right? We used several shortcuts while we were doing this, but there isn't a shortcut where I can just look at that and know the answer. So my advice is don't try to take shortcuts, right? Do one small step at a time and write down every single step. Anytime you're dealing with radicals or exponents. Okay. Let's look at some addition property for radicals. Here I'm going to do the square roots first. What's the square root of 9? Square root of 4? And 3 plus 2 is 5. Yeah. I want that one. There we go. All right. If I do the addition first, what's 9 plus 4? 13. Square root of 13, is that 5? No, these things are not equal. In general, correct. When you're multiplying, that's the same. You can do it in either order. When you're adding or subtracting, you cannot, right? So radical x plus y and radical x minus y cannot be simplified. You can't do anything to make that look nicer. You just have to leave it. So we put a few more lines in the equal sign. Right? Okay. You can add and subtract radicals if they are like radicals, if they're the same. So radicals are like only if they have the same radicand, same number under the radical, and the same index. So here's an example. If I want to add 5 root 7 plus 3 root 7, root 7 is like a like term, right? 5 root 7s plus 3 root 7s make 8 root 7s. Okay, so you just add the coefficients. It works just like if you wanted to add 5x plus 3x. You just add 5x's plus 3x's makes 8x's. Okay, so you got to be careful. Just make sure you don't, the 7s did not become a 14. They did not become a 49. They just stay the same. Okay, so here's how we simplify radicals that do not, at first glance, look alike, right? If I want to do root 12 minus 2 root 75 plus 7 root 27, at first glance, I would say can't add them, they're not alike, right? But I could simplify them first. So these are square roots. So if I want to simplify these things, for root 12, I would rewrite it. I want to ask myself, are there any numbers in the list of perfect squares that divide into 12? 3 is not a perfect square. You're thinking of 4, yeah. So I'm going to rewrite 12 as 4 times 3. And again, one small step at a time. I'm not going to try to do too much. Minus 2 times the square root of, all right, let's try to simplify 75. Yeah, 25 goes into 75. 25 is a perfect square. Goes into 75 3 times, so this is 25 times 3. And then I have plus 7 times 9 and 3, right? You go through your mental list of perfect square numbers or your physical list of perfect square numbers, and you go, does 4 go into 27? No. Does 9 go into 27? Yes. So we write that as 9 times 3. Okay. Now, the numbers that are perfect squares, I can take the square root of, right? What's the square root of 4? 2. So this is 2 times the square root of 3 minus, what's the square root of 25?
5.
So this is 2. I just copied that 2 down, times 5, the square root of 25, times the square root of 3. Plus 7, I just copied that down. Square root of 9 is 3. And the square root of 3, I have to just leave a square root 3. And I'm out of room, of course. Okay. All right, so 2 root 3. And then here I have minus 10 root 3. And then plus 21 root 3. Now, these are all like terms. They're all something times root 3. So I can just add the coefficients. 2 minus 10 is negative 8. Negative 8 plus 21 is 13. Yeah, 13 root 3 would be the final answer there. Yeah, so I'm adding the coefficients now. So if this were, think of it as doing like 2x minus 10x plus 21x. And you were combining like terms. You do 2 minus 10, which is negative 8, plus 21 is 13. So now instead of an x, you're putting a root 3 there. So you do 2 minus 10 plus 21, and you end up with, instead of 13x, you get 13 square roots of 3. Okay, so remember that when you're under a square root, there's like some imaginary parentheses there. You should always do what's under the square root first. So if I do 5 squared, I get 25, right? And then the square root of 25 is 5. Yep. All right, what if I have negative 5 squared?
It's still 25.
It's still 25. So the square root of 25 is 5. So that's a little different than the rule. We thought that square root and squares cancel. So I would have guessed that negative 5 would be the answer. But it came out to 5, right? So it actually came out to the positive value. So what mathematical thing makes negative things positive?
Even multiple. So if I'm multiplying it times an even number, like
yes, squaring or raising to the fourth, yeah, that makes things positive, right? Yeah, squaring makes things positive. Is there any other mathematical thing that takes a negative number and just changes it into the positive version of that number? Negative times a negative is a positive. Correct. That's why squaring always makes things positive. Yep. Oh, I heard somebody say it. Absolute value. You've heard of it, right? Absolute value makes negative things positive, right? It's so it turned out that when I took the square root of 5 squared, I did get 5, right? So my 5s matched. I had 5 and 5, right? But over here, I put in negative 5, but I got an answer of 5, right? So it turned out that it was the answer was the absolute value of what I put in there, right? It was the positive version. So that happens when you square root things because of that squaring thing where negative times a negative makes a positive. But what if it's odd? What if we are cube rooting? Like, so if I want to do the cube root of 5 cubed, that's the cube root of, what's 5 cubed? 125. And what number do you cube to make 125? 5. Right, so it looks like my numbers matched here. I put in a 5, I got out a 5. But let's see what happens when I do negative. This is the cube root. What's negative 5 times negative 5 times negative 5? Negative 125. Can we think of a number that when you cube it, you get negative 125? Negative 5, yeah. Negative 5 times negative 5 times negative 5 makes negative 125. Yeah, Chantal. Yeah, yeah. Yeah, if you divide the 3's, you get to the first, right? And you get negative 5 to the first. Yeah. So our rule, we thought, was that you should just divide, right? And it turns out that that works when the index is odd. You can just do the division, right? If the index is even, you do the division, right? Because this is a little square root here, but you have to make that thing positive, right? So there's actually like one extra little step to the rule that we didn't notice before, and now we know, right? So we have it written down here. It turns out if you take the nth root of something raised to the n, you always get that something, right? Nth root and raising to the n cancel if n is odd. Okay. But if n is even, if you take the nth root of something raised to the n, your answer is just, it's not just plain old a, it's the positive version of a, or the absolute value of a. Okay. So I know this is crazy, but it's a small detail, but it's important. All right, so we've got a couple of silly phrases to help us keep these straight. When n is odd, you end up where you started, right? If n is odd, don't modify, right? And when n is even, you always end up with a positive number, even if you plugged in a negative. And it says if n is even, absolute value gets its revenge. Okay. So updating our shortcut from earlier, when you're raising to the k and taking the nth root, you can just divide, right? Unless n is even, then you do divide, but then you have to put the absolute value bars on. You have to make it positive. All right, so let's do an example with this because it's been very theoretical so far. The 6th root of x to the 30th. Good, x to the 5th. But let's write out all the work. Like, so how did you come up with x to the 5th so fast? You divided 30 by 6, so you get x to the 5th. But I'm going to write it all out. I'm going to write this as something raised to the 6th, right? Because 6th rooting something to the 6th is easy, right? So how could I rewrite x to the 30th as something to the 6th power? X to the 5th, because 5 times 6 is 30. And then the 6th root, and the 6th power cancel, but because the index, because that power is even, my answer is not plain old x to the 5th, it is the absolute value of x to the 5th. Has to be positive. Yes. You need the absolute values. Because the radical was even. No, what I got doesn't matter. It's just whenever you have this index being even, like when you square root, because the index is 2, it's even, you might get a negative, there's a negative number that you could square and get the same answer. So you have to make sure you say, I only want the positive one. Correct, like in this next example, right? If I want to do the 9th root of x to the 36, it would be helpful if I rewrote x to the 36th as something to the 9th, because then my 9th root and my 9th power will cancel. What should I put in there? X to the 4th, yeah, right. X to the 4th, because 4 times 9 makes my 36. And then my 9th root and my 9th power cancel, and I just get x to the 4th. And in this case, I don't need the absolute value because the index, the 9, was odd. It's the index that you have to worry about being even or odd.